Welcome to our structure-sponsored webinar, Integration for Baseplate Design and Anchor Reinforcement by IDEA StatiCa. Thank you for joining us. At any time, you may adjust your audio using any computer volume settings that you may have. This session will be recorded and made available later on the Structure Magazine website. On the bottom of your screen, you will see the Q&A pod. To send a question, click in the text box and type your text. When finished, click the send button or push enter. All questions that you submit will be addressed at the end of the presentation. We are joined today by our speaker, Dave Eckroat. Dave is the VP of Sales and Operations of IDEA StatiCa US. With over 30 years of experience in the structural engineering industry, Dave has worn multiple hats, ranging from construction inspection to design to structural engineering software. At this time, I will turn the floor over to Dave to begin the presentation.
Thank you, Amelia. Hello, everybody. Thanks for joining us today. Let me go ahead and just kind of quickly show you an agenda. So what we're going to cover today is just a very brief introduction to IDEA StatiCa. I know we have a lot of people on the webinar. Probably most of you aren't users, may know a little bit about IDEA, so I just want to kind of give you a better understanding of what we do and how we can help your projects. We will talk about anchor failure modes and some current solutions. We'll talk about our complete baseplate workflow and also show a demo of how the workflow can be used. Then we'll go over some next steps as far as, if you want to kind of test out the software yourself using our trial version. And then finally, we'll jump into some Q&A. So first, IDEA StatiCa, we are obviously a structural engineering software company. We focus on the details of structures. So we have a couple of different products that we offer. One would be our steel license, which includes our steel connection design tool, which is probably what we're most known for at this point. There's also a member application, which is really meant for doing some specialty analysis, especially when you're getting into lateral torsional buckling. So looking at different members. The key difference here versus kind of your general purpose software is that you can model the end connections and take that stiffness into consideration in the analysis itself. Next, we have our app Detail for concrete discontinuous regions. So kind of corbels, walls with openings, openings in members, walk-in columns, deep beams. So it's really a tool meant for kind of specialty looking at concrete elements. Again, using finite element analysis as all of our software does. And it's really kind of an alternative to using strut and tie method. So if you would typically use strut and tie, you can now use Detail for those types of applications. And then finally, we'll talk about the integration between connection and detail. So this is what we're going to talk about all today, for the bulk of today. So really what that means is that you're able to design a base plate within connection, check the anchors, check unreinforced concrete element, pedestal, foundation, whatever it may be connected to. If you still are having some issues with the anchors as far as for pullout or concrete breakout, you can then send that to Detail, model in all your steel reinforcement in the concrete element, and then analyze and design that element itself. So let's jump right into look at some baseplate design. So currently, and what we've had in the past with our connection application is you're able to design the steel base plate, the anchors, welds, shear lugs, including a grout bed, standoff distance, and then the unreinforced concrete block. So if we just kind of look at some examples of this, you can see some kind of more standard type base plate designs. It can also be used for other applications such as maybe an embed plate or an anchoring plate to a concrete wall for a steel beam, those types of things. So here's just some examples of kind of what you can use the connection for the anchor plate or base plate design. So now if we look at the failure modes from ACI, specifically looking at concrete or a connection rather, I'm sorry. So we can kind of see here from ACI, there's different, failure modes for different loading. So tensile loading, shear loading. And what you can notice is that, the green checks are what is done within steel connection. The obviously red X's aren't being checked. And anything with the yellow triangle is we're checking it per ACI formulas, but it's really only looking at unreinforced concrete. So this is something, we've been doing this for several years, and we've realized that there needs to be kind of the next step for those analyses. And where that next step would lead would be anchor reinforcing. A lot of times you're running into projects or specific situations where you need to use reinforcement to anchor the breakout cone in order to achieve shear strength as well as ductility. Anchor reinforcements permitted by ACI 318, section 17.5.2.1. So you can basically structurally transfer the shear from the anchors to the foundations. Also, there's some references in the ACI Design Guide 1. And there was also a paper back from 2013 just discussing strut and tie methodologies for anchor design. So that's kind of what we're going to be able to do now within our detail application. So let's look at kind of how that would all work. So again, you start in our steel connection app, you're modeling and designing the base plate. You can run your anchor checks and you find that your anchors aren't working. And the reason they're not working is that you're getting pull-out, breakout failures. At that point, what you can do is there's now this RC check button in the ribbon at the top of the screen. So once your base plate's designed, you can hit that RC check. It's going to export the base plate and the loadings into, and the concrete element into our detail application. From there, you're going to model in the reinforcing. Then you can run the analysis and review results and then optimize your design from there. So if we look at those failure modes again, we discussed what can be checked in the steel portion, which is on the left side. On the right side now, you can see that all of the things that we weren't able to check within steel can be checked within detail. So whether it be concrete splitting, bond failures, pry out, all those different modes can now be checked within the software using steel and detail. If we look at some other cases that we can check within detail, use of adhesive anchors, you can add those into your model. Shear lugs, base plates with shear lugs. I know that they typically get used on some, specifically higher loads, shear applied base plates. And then also your beam to concrete wall connections and embed plates. So those are just some different cases that you're able to use within detail. So now we're going to jump into the demo. We're just kind of using this column load, and we are going to I'm going to invite Andrea to kind of jump in here and provide the demonstration herself.
Okay, let's start with this demonstration. Today I'm going to show you how to design a base plate and the cross section that we'll use for the column is a W section 14 by 90. The pedestal cross section needs to be 38 by 38 inches, and we're going to use a height of 96 inches to demonstrate the development length check in IDEA StatiCa applications. Here I'm calculating the minimum area of reinforcement, and I'm using 5% of the area of the concrete. So what I calculate as a base is 10 rebars, 10 longitudinal rebars number 8, and I'm going to use that as a base for the pedestal reinforcement. right? Then I am going to use these two load combinations. One of them is with a tension force, and then the second is with a negative compression force on the column. And then both combinations have this huge moment on the column, right? So let's jump into IDEA StatiCa Connection. So for this example, I am starting from IDEA StatiCa Connection standalone. So when you open the launcher, you will use this application, okay? So now let's jump into the software. So here you can see the interface of IDEA StatiCa Connection. For those that haven't used the application, we are always working with one working point, all right? So we are studying just one node, and you can start adding as many members as you need in your joint, all right? You can add more new members here. For instance, if you have a bracing together with this column, you can just add this new member. In this case, I already have the column. It's 14 by 90. You can change the cross section from this area and pick and choose from our database, right? Now, the way we add connections into this joint is by using operations. So let me show you what are the available operations. You can see here that we have standard connections, gusset plates, clip angles, shear tabs, and other operations that will help you to add different details to your connections. In this case, I'm going to use base plate operation. I have already modeled that, so let me activate this base plate operation. That base plate operation has everything inside. The base plate itself, anchors, welds, and all the details you need to specify for this base plate, right? So I'm defining a base plate of 1.5 inches. I'm defining the dimensions over here. And then you can also pick the type of anchor you want to use. So you can add or select another grade from here. And an important thing to mention here is that depending what type of anchor, that's going to be the selection in the concrete application. So in this case, I'm using washer plate rectangular type. So that means this is going to be a cast in place anchor. If you select straight, the first option here, that will be converted into an adhesive anchor in detail application, okay? So that's important to mention. You define the position of the anchors from this area. You can use this operation or use a table under the editor. You can use X and Y position. It's up to you what you prefer. Also, we define the welds from here. You can define from fillet welds, CGP, PUP, either for flanges or webs. And then we have here also the definition of the foundation block. So we're using a 4,000 PSI. So you can change this concrete capacity, right? From here. And we also can define the size of this concrete block. It can be square or rectangular. You can define different offsets. So that will be from the different edges of this base plate. So in this case, it's a square shape, but you can define a rectangular shape from here. We also define the depth. In this case, this is going to be 8 feet, all right? And you can define how to transfer the shear force. It can be through a shear log if you have a high shear force and then you want to use a shear log to transfer this huge shear force, or as we are going to use now, is going to be through the anchors, right? There is a way also to define a layer of grout, so that will be mortar joint or a gap between the concrete and the base plate. I'm going to use direct standoff, right? And finally, here we need to define the load effects. So you can add multiple load combinations, okay? In this case, we're going to just use 2 of them. So the load effects or load combinations, you will input the reactions on members. So you can see that we are adding this axial force on the column, then shear forces and moment forces on this. And then you can activate the, you can see this representation of the forces. And then you can see the direction of the forces. Also, you can activate the labels for the local axis, so you understand what are the negative and positive signs. So I'm going to add this to load effects to this connection. And with that, I'm ready to run the analysis. So I'm going to hit calculate. And let's take a look at the results. So here we have a summary, and you can see clearly in this view what is failing and what is passing, what has a warning, right? So the anchors are clearly failing because they are in red. The green color means this is between 95% and it's under 95% of utilization. So we are just under the limit. And yeah, the welds are in the warning area, but still they are below the resistance, right? So we're good with the welds. It's at 99.0. So to really review the results, you jump into the check tab, right? So you click over the check and you can look at the stresses and then the form shape. So that can help you to understand how is the behavior of the space plate. So you can see that how this is deforming, okay? And this is your first sanity check. Then for every element, we have a tab, and then you can check the results from here. And then if we jump into the anchors, I can also activate the anchor forces or the ball forces calculated in the analysis. You will see the tension forces graphically in this area. And we can sort the results by the maximum tension force, for instance, right? And then we're going to have some different checks here, and the forces and utilization ratios. But to really review those results, we can go into the plus icon, and then we can right click and print preview. So you will see the report for each anchor, okay? So let's take a look at the worst case scenario. And another important thing is that here for each element, you will see what is the critical force. So for this anchor A8A, the LE1 combination was the critical force for that, right? That was a governing combination. Now, if we look at the report here, you can see the anchor tensile resistance. So in reality, we are okay for the anchor tensile resistance. So that anchor selected is its capacity is 84, and the force that we calculate from the analysis is 71. So that's fine. The anchor itself it's okay. But if we scroll down here, we can start looking at the results for concrete breakout resistance of anchors in tension. So we can see that this is no good, right? So that's when we need to start deciding what to do with this design. Even if we start increasing the size of that anchor, that won't help, because this has to be with, or this is related to the concrete breakout cone area, and that's the area that we have. Probably we have a limited area. We cannot increase the concrete blocks, so we need to decide what to do with that. You can also check the concrete pullout resistance. That's all right for that anchor. Concrete side face blowout. The shear resistance is fine, it's passing. Concrete pry-out resistance 2. So the only problem we have here for this anchor is the concrete breakout resistance of anchor in tension. So you can keep looking at this, reviewing your results, and in this case, as we mentioned it before, if we go to the solid view, this concrete block is considered unreinforced, right? So if you know, like in ACI, it tells us that we can use the reinforcement to comply with the concrete breakout, right? So here is not considered. So now we can jump into our detail application and then check this concrete block, including reinforcement, right? Or considering the reinforcement. To do that, we can click over the RC check button, and that will create a detail application file. So we save this file, we click save, and now detail application will be open. Okay, now we are in detail application. So you can see that the model was imported into our concrete application, and then we can start looking at the different details imported. So here you can see the solid block. It has the same properties that we picked from connection application. You can see that we have this support defined in the surface number 5. So the surfaces are defined with brackets in this visualization area. And then we can jump into the transfer devices. Same for base plate, same properties we selected from the application. And then we can start looking at the properties of the anchors. So you can see the same material, same diameter, and because we selected anchor with washer plate in connection, this was selected as a cast-in-place reinforcement. So if you select a straight type of anchor in connection application, the setting is going to be defined as adhesive anchor, right? Then the washer plate is defined with a perfectly bond connection. So this anchorage type defines the connection from the end of the anchor to the concrete block, all right, or the concrete material when we run this analysis. Then also we have some geometry properties. Again, this is imported from connection. So we don't really have to do anything with this information that was imported, just double check, okay? And then also you can start looking at the load cases. So the forces in this base plate and the anchors were imported from the analysis in connection. So you can see that we're importing the forces coming from the welds into the base plate. So in that case, we distribute the force into the base plate in a more realistic way, right? Then we are also importing these forces here into the anchors. If you remember, we have a 75.12 kips in one of the anchors. So this is the force that is going to be transmitted through the anchor and then to the concrete. I know that we have this downwards force, but in reality, this is a tension force. So don't worry, it's a tension force in this case. All right. And then you can also review the other load cases. So these are the load cases. If you need to add an extra load here, you can do that by clicking over the plus icon. So you can add surface loads, point loads, group of forces, and even self-weight. So self-weight is not considered in connection application, but here you can consider the self-weight. So you consider the self-weight of the concrete block. This is important when you have a foundation set up in the soil. So if you use a compression only a spring support, it's important that you use the self-weight in case you have a moment force in that foundation, so it doesn't like rotate and stop the analysis. So that is important when you have this spring support. But in this case, we don't have that, so I'm not going to add that. Then you can see that here we have the load combination. So in this case, the load combination has a factor of 1 because those forces were imported from analysis that already had a factor. So those reactions that we put in connection, they were from a combination with factors. So we don't really have to put factors here, but this is just in case you're starting the model from scratch in detail, right? So we have that possibility. All right, so again, we don't really have to do anything with all this setup because it's information you model from connection. The only thing we need to add is the reinforcement, okay? So to add reinforcement into this model, we can use this operation that's called rebar assembly. So we click over there and then we use group of bars. Here in the group of bars input, we can start defining the diameter of rebar. So this will be a number 8 rebar. And we can start defining from what surface we're going to set up this rebar. So I'm going to start with number 3, surface number 3. You can see that's in brackets. So I'm going to pick that. And then the H will be 4. So the definition of that rebar group is going to be from the H4. So we pick 4 here. So it goes through the top and bottom. So you can define where it starts if you need to short out this rebar from these bottoms here. So you have different options. Then if we look at the top view, right? So we can define the distance from the surface, which is this face of the cube, the number 3, to the position of the layer of rebar. So you can input this surface cover here. I'm going to use 3 inches, right? And then also you can define the cover from the H. So now it's from the H number 4. So you can set up this input from user value instead of the settings. So I'm going to use also 3, all right? 3 inches. So you can see that now it's 3 inches from the H. Now this layer is going to have 4 bars. So I'm going to use 4 bars here, and the distance between them is going to be 10.5, right? I'm going to use 3/8 here, all right? So we can equally distribute this rebar. Now I can rename this group of bars because this will help me later when I am reviewing the results, okay? Now I can copy this group of bars to the next surface. I'm going to use surface 1 now. Surface 1, right? So now the name is copy as well, and now it says vertical 2. Then later I'm going to copy that and put it on surface 4. Surface 4. But instead of 4 bars, I'm just going to use two bars in this surface because we have already some of them in the corner, right? So the H cover is going to be 12.5. Now it's equally distributed there. So I'm going to also copy now this and put it on surface number 2. Surface 2. All right. So now we have this vertical rebar. At the top, I'm going to use basic anchorage. So there is any kind of restriction between this start of the anchorage to the concrete, but at the end it's going to be continuous. So this means this is continuous through that surface, so it's the same. It's perfectly bonded, okay, to that to this area. So I'm going to do the same for all of them. All the groups. All right. Now let's start setting up the stirrups. So I'm going to add a new rebar assembly. And then for the stirrups, the easiest way is to set up from more edges. So on surface H, on more edges. So that will be from surface number 6. And now you can define different edges. In this case, it's 1, 2, 3, and 4. So you can see 1, 2, 3, and 4 here, right? Oops. But this is going to be, we can set up this 180-degree hook or 90-degree hook, all right? Again, that setup is to define the connection from the end of that bar to the concrete, okay? But in this case, the syrup is going to be number 3, okay? So we have that. The surface cover 3 inches, that's fine. And we can say 2 inches from the edges, right? So now we are going to add more layers here. So I'm going to add 10 layers, and the distance between them is going to be 6. So probably we'll need more layers here, like that. All right. However, I'm going to keep adding this stirrups to tie also this 4 here and this 4 vertical rebars. Okay, so I'm going to model that. Let me rename this. I'm going to call it stirrup 1. And I'll continue modifying this. Okay, now I finish the setup of the stirrups. I added some internal stirrups. So you can see that we are tying all the vertical reinforcement as is required from ACI, all right? So now we are ready to run this analysis. But before doing that, because we're just testing the minimum required reinforcement for this pedestal, right? And we're just testing. I'm going to change the settings here, and I'm going to change the mesh settings. So I can use this multiplier to increase the size of the mesh so we have a quicker analysis, right? So we can define it from 1 to 5, and this will define the size for all the model. So I'm going to use 5 for this like initial iteration, so we have quicker analysis. We review results, and then from there we kind of decide what to do. All right. So once we define the reinforcement, we just hit calculate, and let's wait for the results. Okay, once it finished, in the top left corner, you will see the status of the results for each check. In detail application, you get concrete and soil strength checks and the anchorage check, which is translated into the capacity of the steel rebar to develop the force into the concrete. In this case, the analysis stopped at 77% of the applied loads for LE1. By default, the stop at limit strain is active, so that will stop the analysis when one of the strain criteria is reached. See that the zero reinforcement criteria was the first to get to 100% of utilization. However, concrete and anchorage is also close to 100. Let's review the results. So we click on the check tab, and once we click on the check tab, we get the view of the stress flow. So you can see that we are in the summary results and then the stress flow icon. The red lines are representing the compression vectors in the concrete. The reinforcement is taking all the tension, and the blue contour represents the utilization, as you can see here. By using 3D FEA, we can clearly see the real concrete cone failure. Usually, we idealize the cone, but in this case, you can see how the anchors that are loaded in tension and how that is resulting in a cone failure due to the compressive forces in the concrete. So we can activate the forces to see what are the anchors that are in tension and how is that resulting failure cone. Now let's jump into the strength results for concrete and reinforcement. So we click over the strength icon, and then we're going to start looking at the concrete results. For the concrete check, we compare the calculated compressive stresses versus FC limit, which is equal to the concrete strength selected reduced by a material factor of 0.75. Also, we can look at the calculated stresses. You can click over the FC, and we can see the stresses outside and inside the concrete block. To look at the inside results, you can click over the section view and create a new section view. I already created this. So basically you need to select a plane where to locate this section view. And in this case, I located this plane where we have the anchor's intention. I'm going to turn off the loads here so you can see it. To look at the steel rebar strength check, we need to now change to this new reinforcement view. I'm going to turn off the section view, look at the 3D view, and we are looking now at this utilization ratio. Similar, we are comparing the stresses calculated in the reinforcement versus the Fy limit. The Fy limit is taking the strength of the steel for that reinforcement that we selected, and we multiply by a factor of 0.75. You can change the factors under settings if you need that. You can also see the actual stresses calculated in the reinforcement by clicking over this Fs. This gives you an overview of what are the most stressed rebars. Like in this case, the most stressed rebars were the ones close to the anchor's intention. Also, you can look at the results using this table. That's why I renamed the group of bars. And it's easier for you to identify the results and look at the different values that the software is calculating. Finally, we jump into the anchorage results by clicking on this icon. And to explain this, let's talk about the anchorage results and definition. As engineers working with ACI, we are used to calculate development length. But if you look at the code, you can see that the definition is based on the bond stress over the length of embedment of the reinforcement. In IDEA StatiCa Detail, the bond stress is explicitly calculated, and we can also learn the force developed along the bar. So here we are looking at the check utilization ratio, and that's comparing bond stress versus bond strength. And you can also turn on this F total, which is the force developed, the force developed along the length of the bar, and how it's going to develop into the concrete, right? You can also see results by this table in this area and sort out the most utilized reinforcement in terms of anchorage. Now, for this example, the analysis stopped at 77% of the applied forces, right? So what I did here is I did a copy of this model, and I added reinforcement for the anchors so they can transfer the forces into the concrete. So to do that, again, I copy this model, and here, using the group of bars operation, I added these tension harpings. Okay, so I was following the recommendations from ACI, having these harpings close to the anchor's intention, right? So you can see them here in the top view. They are really close to these anchors that were in tension. And also I use a number 5 bar for these anchors, okay? For this reinforcement for the anchors, okay? I also added a hook at the end of this reinforcement. And here you can see the length of this reinforcement. All right. So in this case, I'm not showing all my iterations, but in the presentation, you can see the different iterations I did. I tried out using tension harping without this hook, and I was testing different lengths, so you can see how the anchorage is changed and how you can relate this to your development length calculations. But anyway, this is the one that worked for me with this 90 degrees hook. And then I have 30 inches length in total for this harping, right? And now if we look at the results, we can see how those tension harpings are engaged by the forces that are transmitting from the anchors to the concrete. So we can look at the strength view and then reinforcement. Turn off the section view here so we can see the utilization. You will see how you decrease a little bit the utilization in the vertical rebars, and now the tension harpings are taking more forces, right? So basically you're helping the vertical reinforcement to develop the force from the anchors into the concrete. Okay, so we are happy to share this model with you. If you want to look at it, you can look at the different results with this solution, so you understand how IDEA StatiCa Detail works. Also, reach out if you want to see a different demonstration of the software with a different case. We're happy to set up this meeting with you. All right. Okay, let's wrap up the presentation. And thank you for watching this video.
Okay. So one thing that was not in the demo was kind of the reporting. Obviously, that's always important to kind of be able to produce reports. So just some screen grabs here of what the reports show. So again, your model properties, some 3D views. If you're familiar with IDEA, you know that we like some graphics in the reporting. So as you kind of go through the different parts of the report, applied loads, the results, summaries, reinforcement stresses by the different rebar groups, and then even bond stresses. We do report all of that information out, and it's very comprehensive as you're reviewing your designs. So as we continue to look at our detailed 3D, really we did a relatively simple demo as far as for the example, just kind of showing a pedestal, but you're able to look at pedestals and isolated footings, different corner conditions, pedestals within walls, strip footings. So there's a lot of flexibility within the software. It's not just one specific option that you have. So yeah, just in summary, the IDEA StatiCa anchorage and base plate design workflow simplifies the process by reducing the time spent in different applications to design steel and concrete portions of your structure. It also reduces your manual inputs, and really there's no limitation as far as geometric inputs or loads. And then finally, one of the key benefit of Detail is just the clear 3D visualization of the reinforcement model and being able to see that stress flow. We all like to talk about stress cones, but this is actually, you can actually visualize it within the analysis. So now let's just look at some next steps. So definitely we have a lot of information on our website, whether it be sample projects, blog posts, tutorials, even the theoretical background. Also, if you're not an IDEA StatiCa user and you'd like to try this out, we do have a trial available right on the website. You can use that for 2 weeks at no cost and kind of put it through its paces and see how it could be helpful for your projects. One thing that we are doing for webinar attendees is that we will be sending out an email next week, specifically for US and Canadian attendees, that there will be an exclusive offer for you from IDEA StatiCa related to the anchoring option. Also for PDH continuing education requests, so there's you can either scan the QR code and fill out the form there, or you can go to the link that we have below there as far as for the PDH requests, which we will do our best. I know we have a lot of attendees on this webinar today, so we are hoping to get those out within the next week or so. So I will leave this screen up for a second, and we can start to look at the Q&A.
As a reminder, the Q&A pod is located on the bottom of your screen. To submit a question, type your question in the text box, and when finished, push send or enter.
Okay, so just kind of looking through some of the questions here. I also have my colleague Johan to kind of help me with some of these. So the first question was just, does it also design the footing? That we only had the pier, and yes, that was kind of in the thought of time that we just did the pier design. But you can, as we showed in one of the examples, you can do both the pier and the foundation. Next question. Can you use the Canadian code, CSA A23.3 as well? I'm gonna have to defer. Johan, do we have the Canadian code in detail at this point?
Not in detail yet, but we do have it in connection. So if you want to start by designing the anchors with unreinforced concrete, at the moment we do have that for Canadian code, but for Detail 3D, we are currently working on adding more international codes. We do have European code and AISC code, US code.
Okay. I'm just trying to see. John, were there any questions that you wanted to answer?
Yes, so basically a couple of questions if we are able to model circular foundations or circular reinforcement. The answer is we are able to do it through the option of polygons. So if we, let's see. In our options for geometry, we do have the option of polygon, and from there a user can input the different coordinate systems to create kind of like a hexagon or octagon, and from there mimic the circular foundation. Nonetheless, we are working on adding that feature in upcoming versions.
Just scrolling through here.
Are we able to model 135-degree hooks? We are able to consider that. I did send a link in the chat or in the questions where we basically cover the different angles, which are 180, 90, 135, or straight hooks. And within our theoretical background, we're basically go into detail on how we consider each and every one of them.
I see a question, when will anchors without grout be able to be exported to detail? I believe you can do that, correct?
Anchors in, can you repeat that again?
Anchors that don't have a grout bed.
Oh, yes, that can be exported directly into 3D, and then all the forces and information is imported. Can we insert custom hairpin rebar? Yes, that is basically any customization in the rebar. Their geometry can be done in IDEA StatiCa, whether we're referencing surfaces or by inputting its position manually, it can be done.
Another question that we had was, can you change the spacing of the ties at the top of the pier, as ACI requires 2 ties within 5 inches from the top of the pier? Absolutely, this is fully customizable. You can adjust your tie spacing as you go through the section or across the height of the section. that's not a problem at all. It's fully customizable.
Here I see another question about anchor bolts. If we are able to add J-shape anchor bolts, yes, the answer is yes, we are able to offer J-hooks as one of our anchor types. As well as that, to mention that we are also able to model custom anchors as well as their material properties in case you want to bring in those properties from I believe one of the questions mentioned Hilti, so we can input the material properties.
I see the question as far as, do we have a course or online training for how to use the software? We definitely have tutorials online. We are working on some training courses, specifically related to the anchoring design. We will definitely make sure everybody knows when that is available. But obviously, we always provide great, try to do our best at tech support and being able to help you with your project as well. So even if there's not a formal training, we can always schedule a session to kind of go through it.
And here I see a question about integration. If we are able to integrate with frame analysis software such as STAD, ETAB, SAP, the answer is yes, we can integrate with many other analysis software, not just the ones mentioned. We also are able to integrate with many detailing software so that you bring in your detail base plate connection. I did attach the link to the full list of all the different integrations that we offer. They're all available in our website. You can always check them out.
Let's see. There's a question as far as doing the design with other country building codes. I know we have the Euro code, I believe the Australian code for the concrete design. John, am I missing anything?
No. I think you're covering it pretty well.
Okay.
One question that I believe might be of interest to the attendees is if we can mix and match casting plate anchors with post-install anchors. The answer is yes. In Detail 3D, you are able to mix your post-installed with your casting plate anchors, just to kind of take into consideration RFIs or any last-minute modifications that need to be made, or anchors were misplaced or misinstalled. You can always model all those situations in Detail 3D. And so for the post-install anchors, you could always input the bond strength of those epoxy anchors, and we will analyze those anchors per that strength.
Lots of great questions here. Should detail be a part of the typical steel to concrete connection design, given that connection does not check all the failure modes for ACI? So that's a tricky one, because obviously we feel like you should be using the software that we put out there. At the same time, if it's just a case where you're not getting into that very often, you can get the forces reported out of connection, so you can design the reinforcement by hand. It's probably gonna be a little bit more time consuming, but realistically, we see this as a great workflow to be able to cover all the situations that you would run into around base plates and anchorage. I think we're getting to the end of the questions.
I think so. Another last one that I saw was if we're able to analyze in either ASD or LRFD, the answer is yes. Although for the anchor checks, those checks are per LRFD, but both codes or both designs modes are available, as well as the different editions.
Well, I see many questions asking if we can put the link for the PDH certificate into the chat. Actually, in the email that you'll receive next week, there will be that link to be able to request that PDH certificate. So we're definitely going to be able to help you with that. I think I'm just double checking here, getting to the end. Yeah, so I think we're finished with the Q&A. Thank you again for attending. It was a great response to the topic. I know there was just another webinar on anchor reinforcement related to ACI 2025, ACI 31825 a couple weeks ago. So hopefully this is kind of tying in nicely with that. And thanks again.
Thank you, everyone.
Thank you for a great presentation. On behalf of Structure Magazine, I would like to thank all of you for your participation in today's event. The recording of this webinar will be available on the Structure website within the next week. This concludes today's program. Thank you and have a great day.